Precipitable water and forecasting. Let's begin this video by asking a few questions. In particular, what could high values of precipitable water imply? What might it mean for weather forecasting and things that you're interested in? How might precipitable water values differ across Australia or differ between seasons? And then there are issues of how we might measure and calculate precipitable water. On the right hand side you can see an image from NASA, and it's the global distribution of total precipitable water in millimetres. Where are the values large and where are they small? Take a moment to pause this video and discuss amongst your colleagues these questions. So how did you go? What conclusions did you reach? Larger than average values of precipitable water can imply heavy rainfall potential. Remember that precipitable water is a column integral of the amount of water vapour. And so if all of that is realised, which we would be naive to assume would be the case, but nonetheless, if all of it was realised, the larger the value of precipitable water, the heavier the rainfall potential. Precipitable water values are larger in the tropics than in the mid-latitudes during summer. Remember that temperature controls rate of evaporation, so the warmer the air, the greater potential evaporation of liquid water into water vapour, and therefore the higher the value of the precipitable water. You can see on the right hand side how the tropics, typically being warmer, have high values of precipitable water. Of course, it's not only the surface value driven by evaporation that's important, but if you have convergence driving deep convection, then air with large values of R, that is mixing ratio, can be transported higher into the atmosphere, increasing the values of precipitable water. You can see places like Antarctica, the values are very low. So what would we expect an F160 to look like with high values of precipitable water, or in contrast with low values of precipitable water? Before we get there, let's think about some forecasting issues. When and why would we look at precipitable water field when forecasting? Well, clearly we're interested in the potential for high-end rainfall events, for things like flash flooding and flooding and so on. What does the value actually mean? Well, we need to be very careful with the actual value that's measured from day to day, and what's important to do is not so much that value, but how it compares to the climatological average. If it's significantly larger than the climatological average, then we can intuit that we have the potential for a high-end rainfall event. And likewise, you can't compare the value and say that's going to be the value of rainfall you're going to get. You never rain out the atmosphere entirely. So for example, 25 millimetres of precipitable water does not mean 25 millimetres of rainfall. There are of course other factors that are involved in high-end rainfall events to be discussed in other courses throughout the year. There's lifting, there's the role of surface-based convergence, there's the aerial extent of systems, whether or not they're small isolated systems that rain heavily in one location or rain heavily over a larger area, and then of course there's system speed. So there's a storm or a weather system spend a lot of time in one place and rain a lot of its moisture out in that location, or does it move through quickly and not result in high-end rainfall events? So here's a trace from Rockhampton in Queensland, and you can see the precipitable water value is 61.5 millimetres. Now the trace, both the temperature and the dew point profile, are to the right of the SKU-T log P aerological diagram. So there are high values of the dew point temperature, and these correspond to large values of the mixing ratio, and therefore to large values of precipitable water. For example, if you look at the surface dew point temperature, it's about 25 degrees, which is very humid. If we compare and contrast that to a sonde from Casey in Antarctica, you can see both the temperature and the dew point profile are well to the left of the diagram. And the surface dew point is about -9 degrees Celsius. And so the corresponding mixing ratio is very small. You can see that's about 2 grams per kilogram at the surface. And so when you integrate that through depth, for this particular profile, we get a precipitable water value of 3.3 millimetres, which is very low indeed. So there's not much risk of a high-end rainfall event here. Conditions are very dry. Moving on then, let's look at this mean sea level pressure diagram. What time of year is it for? Well, it's a February plot, and so that's the height of summer, and in particular the wet or monsoon season over northern Australia. So what you can see dashed in across the top of the chart and extending into the southwest Pacific is the monsoon trough, that dashed line. And you can see hashing indicating rainfall across much of northern Australia, Cape York Peninsula, and what's known as the top end, which includes Darwin. Further south we can see the subtropical ridge, and that's been marked in by that squiggly line there, which joins up the high pressure systems. And that's a region of atmospheric subsidence. Further south still, conditions are cooler and there's a low pressure system, which is going to be associated with some convective weather, some shallow cumuliform cloud. It's all behind a cold front, which you can see has been marked in there. Let's compare that to the satellite image. You can see associated with the trough across the north of the chart into the southwest Pacific, there's very bright values indicating cold cloud tops and extensive regions of cloud. This is the monsoon. So we have warm, moist sea surfaces, so the large temperatures can drive evaporation, increasing the value of the mixing ratio near the surface, and the convergence associated with the trough will lift a lot of that moist air aloft. So there'll be large values of mixing ratio through a depth of atmosphere, and therefore large values of precipitable water. Much of Australia in the south is cloud clear, and in the further south you can see there's more cloud, particularly in the Southern Ocean. All that speckledy cloud is convective cloud, but the further south you get, as we've seen already from the Casey trace, cooler conditions imply less evaporation, imply lower values of precipitable water. So let's look at a model analysis of precipitable water. You can see a maximum of 79 millimeters associated with that deep convective cloud sitting in the Gulf of Carpentaria. You can see the axis of the maximum values coincides roughly with that trough we saw on the mean sea level pressure chart and much of the convective cloud. There are very low values across much of Australia, less than 10 millimeters. Remember, that was underneath the subtropical ridge, which is associated with air that's descending. Values are a little bit larger over the Southern Ocean, where we saw that convective cloud, and then they decrease again further south as temperatures decrease. You might want to stop and slide the bar through the video, or sit and look at the handout and compare these in more detail. Here's another example, and this is taken from March, which is towards the end of the wet season. Again, we can see the subtropical ridge across southern Australia. There's a monsoon trough in the southwest Pacific and in the Indian Ocean, and there's a trough over northern Australia extending into central Queensland. So where are the values of precipitable water going to be high, and where are they going to be low? Here's a satellite image, and you can see associated with the trough in inland Australia is some deep convective cloud. You can see a deep convective cloud over Papua New Guinea and the southwest Pacific. And southeastern Australia is under the influence of some very shallow cloud. Oh, I've gone the wrong way. My apologies. So here are the traces now. There's Melbourne on the left, and the precipitable water value is 22.4 millimeters. That's the region where the cloud was quite shallow that we could see. And that's associated with an inversion in the trace. We'll talk about that in a later video. You can see the surface value of the dew point is about 21 degrees, so that's still quite high, but then the moisture is fairly shallow. So above 700 hectopascals, you can see that there's a shift to the left in the values of dew point temperature, and that's going to be associated, of course, with a decrease in the value of mixing ratio. The Darwin trace, you can see the precipitable water is higher. 41.3 millimeters isn't incredibly high for Darwin, but nonetheless, the dew point profile is shifted towards the right, and the moisture is deeper. So the values are are higher there, and there's still the potential for deep convection, for thunderstorms at Darwin, which are often associated with large values of precipitable water. Here's yet another example, and now this is taken from November. This is before the beginning of the wet season over northern Australia. Again, there's a trough in the South Pacific. There's a large high pressure system in the Tasman extending a ridge up the Queensland coast. There's a trough over southern Australia, and you can see that there are northeasterly winds to the east of that trough, and they're going to be dragging in warm, moist air from the Coral Sea across southern Australia. Again, there's the subtropical ridge, and there's a large front extending up from the Southern Ocean. Here's the satellite image now, and you can see the convective cloud in the Pacific Ocean associated with that trough, the convective cloud associated with the trough over southern Australia, the cloud band associated with the front, and behind it that speckled cloud, which is the cumuliform cloud. Here's the Darwin trace, a precipitable water value of 53.2 millimetres, whereas you can see a large departure, or rather what we call a large dry slot in the Adelaide trace. So the values of mixing ratio are reasonably large, say below 900 hectopascals, and above that the dew point profile shoots rapidly to the left, which means that there are low values of the mixing ratio, and we call that a dry slot because the air is fairly dry. And the resulting precipitable water value is 18.6 millimetres. So in this video we've had a little bit of a look at values of precipitable water and how they vary geographically and seasonally.